Hi everyone, welcome back to Rotational Motion. Today we are talking about torque. Last time we were doing like kinematics and things like that. Torque is more about forces and how things relate rotationally for force. Okay, so quick video. So torque is a force that causes or changes rotation angularly. Okay, sorry. Angular version of force. So torque is equal to the force times the radius times sine of theta. So let's say we have a bolt here and we're pulling on this straight down. Okay, we're going to be pulling on a certain amount of force. The more force you put on it, the more torque we're going to be putting on this bolt. And then the radius. So the further we are, if we're all the way over here, we're going to be putting more torque onto the wrench. That's why maybe if you've done things like loosen a bolt, all the way at the end is going to give you more power. And then the sine of theta. So depending on the angle we pull at. So for example, right now, the lever arm is like right here. And if we pull perfectly perpendicular, this will give us the best angle to pull, 90 degrees. Sine of 90 is equal to 1. But if we pulled at like a weird angle, like this way, it'll be hard. And if we pull this way or this way, that just equals 0. So no matter how much we pull, we won't be able to loosen this or put any torque on that. Okay? So T stands for torque. F stands for force, R is the lever arm, distance from the axis of rotation where the rotation is applied. Theta is the angle between the force and lever arm. It's just similar as when we did work, the cosine of theta. It's kind of the same way it works there. Rotating clockwise, we put as negative, and rotating counterclockwise, we put as positive. Okay, moving on. Okay, so for maximum amount of torque, force needs to be applied the furthest from the axis of rotation as possible. Okay, so if you pull on the wrench over here, you're not going to put as much torque as if you pull on the wrench over here. Okay, the further you can get from this rotating point, the more torque you can apply. Okay. Second part, force needs to be applied perpendicular from the axis of rotation. Okay, in which diagram will the wrench exert the most amount of torque on the bolt? That will be option D. And the reason for that, it is completely perpendicular to the axis of rotation. So that's a 90-degree angle. Okay. Actually, this one and this one, no matter how much force you do, you will not put any torque onto the bolt. This one you will, but it's not as efficient because it's not perpendicular. All right, moving on. A 1.1 kilogram wrench is trying to twist a nut. The length of the wrench lies directly to the east of the nut. A force of 150 Newton acts on the wrench at a position 15 centimeters from the center of the nut in direction 30 degrees north of east. What is the magnitude of the torque? Okay, so let's see. 15 centimeters. Okay, so part A. Torque is equal to force times radius times sine of theta. So let's plug that all in. The force is 150. Radius is 15 centimeters. So I'm going to put 0.15 meters times sine. The angle it makes from that is 30 degrees. So let me put that into my calculator. 150 times 0.15 times sine of 30. Make sure your angle is in degrees. Is equal to 11.25 Newton meter. Okay. Part B. If the person starts to pull on the wrench at an angle of 0 degrees, how would this affect the torque? Well, so the angle of 0 degrees means you'll be going like this. That's the force. So that means that the bolt would not move because 0 torque would be acting on it. Okay, sine of 0 is just equal to 0, meaning torque would also be equal to 0. All right, moving on. To open a revolving door, a force is applied at a distance r from the axis of rotation. If the minimum torque required to open the door is 3.1 Newton meter, what force must be applied if the lever arm is 0.94 meters away, 0.35 meters away? Okay. So we're assuming that when we push on this door, it's going to be perpendicular to the axis point, meaning a 90-degree. And you could assume that many times. And that being said, let's try this. So torque is equal to force times radius times sine of theta. The first one, it needs 3.1 Newton meters of torque to open. We were looking for the force, I'm going to say for A, times the radius, which is going to be 0.94 meters away, times sine of 90, and this is just 1. Okay, things to know. Well, when you just think about it, we should maybe think which is going to require less force, A or B. And we should know the further you are, the less force you need to open the door, okay? The closer you are, you're going to need much more force. But anyway, let's figure this out. Force of A, 3.1 divided by 0.94. 3.3 newtons. Okay, part B. Torque is equal to force times radius times sine of theta. Force of B is what we're looking for. Torque is 3.1. The radius is 0.35. And sine of 90 is just 1. So force of B is equal to 3.1 divided by 0.35. And we get 8.86 newtons. Okay. All right. Moving on. It's a good Jurassic Park scene. You should check it out. Alright, 2 children are on either side of a balance beam. One child is positioned 50 meters from the center pivot point and has a mass of 80 kilograms. Okay, so this is 80 kilograms. The other child has a mass of 55 kilograms. Where should the second child sit relative to the center pivot to keep the balance beam from tilting? So the question is, first of all, do you think it's going to be more than 50 meters for this to be balanced? Or do you think it's going to be less than 50 meters? Okay, you could think about it. This person has 80 kilograms and 55 kilograms. All right, I'm going to start to solve the problem. How we're going to do this is we're going to try to figure out how much torque each of these people are exerting onto the seesaw. So I'm going to do the torque of the first person. Torque. So we have this person applying a force, we're going to say perpendicularly, 80 kilograms. So that's going to be a force of 800 newtons, 80 times 10. So that's the force of gravity, which is 800 newtons. Times the radius, he's 50 meters away. And doing it perpendicularly, it's going, perpendicular to where it is. So that's sine of 90. So this is going to be equal to 4,000. 800 times 50. 40,000. Newton meter. What this is also telling me is that in order for this to be balanced, that means that this person also needs to be exerting 40,000 Newton meter of torque. So let's do that. Torque 2 is going to equal 40,000. And this is going to be equal to his weight, so 55 times 10, 550, times a distance we don't know how far he is, times sine of 90. Now, but we can find that R, 4,000 divided by 550, and we get that he is 72.72 or 73 meters. It's a pretty long seesaw. All right. Hope that makes sense. Watch it again if it didn't. Moving on. Alice and Bob are sitting on opposite sides of a balanced plank. Alice is 4 meters away from the fulcrum on the left side. Okay. Alice has a mass of 55 kilograms. What is the mass of Bob if he is 3 meters from the fulcrum on the right side if the plank remains level? 3 meters. If Bob slid his body close to the fulcrum, what would happen? Okay, so part A, let's see, how are we thinking about this? So we did it a certain way before where we found the torque and then set it aside, but what I want to do is I'm going to say the torque of Alice is equal to the torque of Bob, okay? Because if they're balanced, they have the same amount of torque, so I'm just going to set them equal to each other. So Alice's torque, we have that 55 kilograms. So her force of gravity is going to be 55 times 10. So 550. Well, maybe I'll write it out. I'll write it out just to simplify it, just in case people are confused. So I'm going to say force of Alice times the radius Alice is from the fulcrum times sine of theta is equal to the force of Bob, radius of Bob from the fulcrum times sine of theta. Okay, force of Alice is 55 times 10, her weight 550. She is 4 meters away and perpendicular to the axis, so that's just 1. We don't even have to put it there. You know what? I'm not even going to put it there because I don't need to. Force of Bob, we don't know his mass. So I'm just going to put m times 10. He is going to be 3 meters away. And sine of 90 is just 1. Okay, so now let's simplify for this. I'm going to do 550 times 4. Then I'm going to divide by 3. Then I'm going to divide by 10. And then we see the mass of Bob is going to be 73.33 kilograms. Okay. Part B is if Bob slid his body close to the fulcrum, what would happen? So that means that he would have less radius. That would mean less torque. And that would mean that he would start to rise up because Alice would have more torque. Okay. He would start to tip downward. What? He would have less torque. So then he would actually start to tip upward. Okay. Let's change that. All right. Let's look at this next example. Example number 15. So what we have is two forces act on a wheel. The wheel is free to rotate without friction. It has a radius of 0.42 meters and is initially at rest. Given that F1 is equal to 12 newtons and F2 is equal to 9.5 newtons, I'm going to put it over here, 9.5 newtons and 12 newtons, okay? Find the net torque caused by all the forces. So the net torque is, in this case, going to be the sum of all torques is equal to, I'm going to say the torque of 1 plus the torque of 2. Okay, so let's find what the torque of 1 is. Torque of 1 is equal to the force, which is going to be 12 newtons, times the radius. It has a radius, the wheel has a radius of 0.42 meters, so from here to here is 0.42. And the angle it's going to make, so this angle is, kind of gives it to us already, that's going to be 50 degrees, okay? This is the axis of rotation from the middle point right there, okay? And that's 50 degrees. And let's see what we get. 12 times 0.42 times sine of 50. So we get 3.86. But we have to remember, is this positive or negative? So when this pulls over here, straight up like this, which way is it going to rotate? Is it going to rotate counterclockwise or is it going to rotate clockwise? And we should know just by looking at this one, it's going to be rotating counterclockwise. So this is positive. Torque number 2 is equal to a force of 9.5 newtons. And it is again 0.42 meters away. And this angle is completely perpendicular to the axis of rotation. So that's going to be 90 degrees. So let's see what we get. 9.5 times 0.42 is equal to 3.99 Newton per meter. But now if we just look at this angle, this force, would this rotate it counterclockwise or clockwise? And we can see that if we just look at this, it would rotate it clockwise, meaning that this should be negative. So if we add these two together, 3.86, we should get negative 0.13 Newton per meter. Okay. So that's what the torque is. And then part B says, in which direction is the wheel spinning? So if the net torque is negative, that means that this is going to be spinning clockwise. Okay. Hope that makes sense. Moving on. Static. Okay, so when objects are in static equilibrium, you can mathematically put the axis of rotation where you want it to help you with the problem. you should place the axis of rotation in a spot where you don't know what the force is. That's a little tip. And another thing is, in static equilibrium, net torque is equal to 0 and net force is equal to 0, because essentially nothing is moving, nothing is rotating, and nothing is moving back and forth, or nothing's accelerating, at least I should say. Alright, so let's look at this example number 16. A child of mass 43 kilograms is supported on a plank that is 10 meters long with negligible mass. So two people exert the forces F1 and F2 as indicated. Find the forces required to keep the plank in static equilibrium. Okay, so let's write some things down. 10 meters, so this is going to be 7.5 meters, and this is going to be 2.5 meters. This little baby here is 43 kilograms, so force of gravity is equal to 430 newtons. Okay, so something that we should know about things in static equilibrium, meaning they're not rotating, accelerating angularly or translationally. What we should know is the sum of all torques is equal to 0, and the sum of all forces is equal to 0, because there's no acceleration happening. So for now, let's look at the forces. So, okay, we don't really know many forces, so we're going to look at the torque. So first thing we got to do when we do problems like this is we have to put an axis of rotation somewhere. And because it's not rotating, we can actually put it wherever we want. But it's best to put it where we don't know where one of the forces are. So I'm just going to put it over here. I'm going to say this is the axis of rotation. I'm going to put it right there. So now I'm going to find the torque of each of these. F1, maybe I'll do F1, and I'll make this the second one, F2, and the force of gravity. So let's find the torque of each of them. Torque 1 is the force F1. We don't know what that is. We know the radius, how far it's from the axis of rotation, is 0, because it's on the axis of rotation, times sine of 90, because it's perpendicular. So we know that, we don't know what F1 is, but we know this is equal to 0. Torque 2, we don't know what F2 is, so I'm going to put F2, I don't know what that is. We know the radius is, it's going to be 10 meters from the axis of rotation, times sine of 90. And we don't know what that is yet. Torque 3, let's see if we can figure that out. F3, the force of gravity, we do know that, it's 430. And it is 7.5 meters from the axis of rotation. And then sine of 90. So let's figure this out. 430 times 7.5. And we get, and then if we can see this, which way is this going to turn? Is this going to turn clockwise or counterclockwise if this was the only force acting on it? And then we can see that it would be turning clockwise. So this is going to be negative 3,225 Newton meter. And those are all the forces acting on this plank. So now let's go back to torque number 2. We know that we don't know what F2 is, but something that this is telling us is that this has to be positive 3,225 Newton meter, because the sum of all torques need to equal 0. And if we know that, we can now find what F2 is equal to. So now we can find F2 is equal to 3,225 divided by 10. So 322.5 newtons. So that's how much this person here is pulling up on the plank. Next thing is we have to find what F1 is equal to. And how we're going to do that is we should know the sum of all forces is equal to 0. So let me erase some things here. Okay, as I erase those things, let's look at this. We should know that F1, we don't know what that is. F2 is positive 322.5, and force of gravity is minus 430, and the sum of all that should equal 0. So knowing all that, we should find F1, 430 minus 322.5, and we get 107.5 0.5 newtons. Okay, that way the sum of all forces equals 0. And there you go. Hope that makes sense. Watch it back if it was a bit difficult, because there was a lot going on there. Moving on. The figure shows a force P being applied to one end of a lever of length L. What is the magnitude of the torque of this force? Okay, so let's look at this. We know that this is length L, and the P is going to be on the end of this. I'm going to call this force P. And even though we have this angle here, we don't know what this angle over here is. I'm going to call that theta prime. Okay? I mean, I guess we know that this is 90 degrees, but we don't know what this angle here is. But what we should know is that this cosine theta here, if we were to, or that sine theta there, would be equal mathematically to this cosine of theta prime. Okay, because it's a right angle here. So mathematically, we should know what that is. Oh, sorry. I should say this cosine theta is equal to this sine theta prime. Okay. So, what can we do about this? We can say torque is equal to the force times the radius times sine of theta. Okay, so we can say the force is just P. The radius, how far it is from the axis, is length L. And the sine of theta prime is equal to just cosine theta. So that's going to give us B. Okay, needed to know a bit about some tricky geometry math there, but hopefully you guys still remember that. Okay, moving on. Alright, so a little bit confusing here. We have this thing that's all stable and not moving, and we're wondering what M1 is, what M2 is, and M3. Okay, so a lot going on here. Pause it if you want to try to figure it out on your own, but I'm just going to kind of get to it. Okay, so before we kind of learned about how when something is balanced, we can do torque 1 is equal to torque 2, right? Because they're in equilibrium, so the torques cancel out with each other. And then we did the force times radius times sine theta is equal to the force of 2 times radius 2 times sine 2 theta. Well, it's not really 2 theta, but yeah. But if everything is acting perpendicular to the axis of rotation, so if this is the lever and it's in 90 degrees, we can kind of just get rid of this because this is just 1. Another thing I want to say is force of gravity is going to be acting on all of these, so it's going to be like the mass times 10 times radius is going to be equal to m2 times 10 times r2. But we can get rid of this 10 because those two are just going to cancel out on both sides. So anyway, that being said, for this first problem here, I can say m1 12 centimeters times the radius is equal to m2 18 centimeters. Okay, and I hope that makes sense. It's just like a simplified version of the force of gravity. But anyway, if that didn't make sense, then watch it again and hopefully it'll make sense. Or you could just take my word for it. Okay, so we have this first two equations here. The next thing that we should know is we don't know what M1 or M2 is, but what we should know is we could find a little bit of torque on this level over here. We should find that 0.3 kilograms times this 24 centimeters is going to be equal to this side over here, which is 6 centimeters, or a certain amount of mass, the combined mass, M1 and M2, times this 6 centimeters. Okay? And then let's find what M1 plus M2 is equal to. M1 plus M2 is equal to, so I'm going to do 24 times 0.3 divided by 6. And then I get 1.2 meters. Wait, what happened? Oh, 1.2 kilograms. Okay, great. 1.2 kilograms. So I don't know what M1 or M2 is, but I know both of them combined is equal to 1.2 kilograms. So now what I can do is I can combine some of this. Okay, so what we have here is we have two formulas and two variables. We don't know M1 and we don't know M2, but we have two formulas, so now we can kind of figure that out. So how am I going to simplify this? Maybe I'll do it this way. I'm going to say M1 is equal to M2 times 18 centimeters divided by 12 centimeters. And let me simplify that more. 18 divided by 12 is equal to M2 times 1.5. And now I'm going to plug this in over here. So M1 is equal to M2 times 1.5 plus M2 is equal to 1.2 kilograms. Okay, so I have all this, and now let's do some math. So I have 1.2, and then I have M2 1.5 plus that. Okay, so now I'm going to combine these two. We have 2.5 M2 is equal to 1.2. And then I'm going to divide both sides by 2.5. And then I get M2 is equal to 1.2 divided by 2.5. And I get 0.48 kilograms. Okay? And now I could just plug that in over here. If that's 0.48 kilograms, I could do times 1.5. And that would be M1 is equal to 0.72 kilograms. Okay. All right. So now we did all that. I'm going to erase a lot of this just to keep going. And then we're going to try to find M3. Okay. Hope that made sense. I know it was a lot. We did system of equations, which is a harder kind of math thing, but hopefully you're okay with that. Again, try it again, look at it again if it was confusing, so that you feel good about moving on. Okay, so for trying to find M3, what we're going to do is we have this over here, and we're going to do that. So the torque of one side is M3 times this 31 centimeters. And this is going to be equal to the masses of all these objects at a distance 18 centimeters away. So I'm going to do, this is 0.2 plus 0.3, this one, and then what we found, 0.48 plus 0.72, and then a radius of 18 centimeters. So now let's figure this out. Let me just put that in. 0.2 plus 0.3 plus 0.48 plus 0.72 times 18 centimeters, and then divided by 31, and then we get M3 is equal to 0.98 kilograms. There we go. Yep. Alright, so that's mostly it. Next time we're going to be doing a few more other problems, so I hope to see you with that. Thanks for watching, everybody. Bye.